All right, thank you very much. We don't have much time, so I will go straight to the point. I saw that in the title of the conference there is the word sustainability. Okay, so I thought that it would be useful to start with this graph. There's a lot on this graph. I'll guide you through step by step. So what we see here on this line is the historical evolutions of CO2 emissions. At some point, scientists discovered that CO2 is not the only greenhouse gas in the atmosphere and started to measure the other greenhouse gas emissions, and that's the start of the other curve that we see here. So this graph combines data from various reports, and the most important one is the one generated by the IPCC 1 year ago. What they are showing here is the amount of reduction that is needed to maintain global warming at 1.5 degrees. Those scientists understood that we are not able to reach this goal, so they also show us another curve, which is the maximum 2-degree target. Maybe because these scientists know humans too much, or they have a good sense of humor, they also show us the top curve that we see there, which is what will happen if we keep doing business as usual, if we keep doing research as usual as well. This is not +2, +3, +4 degree targets. It's impossible to predict. We only know that all tipping points, climate tipping points will be reached, and we also know that it's not an environmental crisis anymore. It will be an environmental collapse with all the economic crisis, social crisis, and human crisis that would follow. On this graph as well, we can see that the only time in history where humans have been able to reduce greenhouse gas emissions is during, also the only moments are during crisis. So we have, for instance, oil crisis in the 60s, at the end of the 60s. We have the financial crisis of 2008, if you remember it, and I'm pretty sure that you remember the COVID crisis as well. So what it means is that if we want to achieve these reductions here, we will have to go through a crisis. We are not used to see the two parts of these graphs together, but it gives a sense of rate. And of course, as was presented earlier, the construction industry has a big role here. So what I want to say here is that there are two paths. Either we keep doing things as usual, but then it's the environment, nature that will guide the crisis, and we will have to follow and adapt. Or, the other pathway is that we try to create this crisis, and at least with the hope that we could control some aspects of it, and probably most importantly, just the social aspects of it. In both cases, it's kind of a bad news for this symposium. There is no future for construction. Thank you for the invitation. My talk is over. No, what I mean here is that there is a very high probability that all the things that are presented in this symposium this year will pretty soon become irrelevant, and sooner than expected. So how to limit construction, how to limit demolition, it's a very hard question, and I believe that my colleague and next speaker, Charlotte Malterbart, will go into much detail and with more nuance into that than me, so I will stop here. As far as I'm concerned, I only have partial answers, and one of them is related to an opportunity that is missed at the moment, right now, today. This map shows all the buildings demolished in the past 20 years in Switzerland. There are 70,000 of buildings demolished. And what I want to highlight here is that those buildings are not demolished because the materials was degrading, because it was of bad quality. Those buildings were still sound, and structurally sound at least, and for good quality. The reason why we are demolishing them is because of real estate investment, because some people decide that there is a need for the buildings. But this material here, there is a lost opportunity if we are not reusing it. And so what I mean here is the reuse of components. I'm used to give this example because it shows all aspects in a very clear way. So that's this little story of this bridge built over the Rhine, the border between Switzerland and Germany. Built in 1810, 100 years later, the city decided to replace that bridge with a bigger one, a taller one. And a few months later, at the same time it was being dismantled, monks from the village nearby decided to reuse the pieces. So we can see the posts in the bridge here are actually these ones. We can actually see here the cuts that were there before. So they used them to build this barn. This barn is still in use today. The picture dates from 2019, but it's still there. So what we have here is a building that is 100-year-old. It is made with components that are 200-year-old. And that's probably the future of construction. We should, one aspect of the future of construction that we should emphasize. And as was mentioned earlier, most of the answers for the future are already there in the past, and probably we don't have the time to create and test new technologies. So in terms of impact, what would component reuse bring if it's well done? Well, not all types of reuse, but for certain types of reuse that I will show at the end of my presentations, per product, we could reduce up to 90% of greenhouse gas emissions. That's huge, as you will see. If we reuse all waste in Switzerland, we can reduce up to 40% of waste. We could save 10 to 25% of extracted materials, only that, but still it's not nothing. So reuse is only one solution, so of course it's not the solution. And reuse contributes to the piecewise recovery of heritage, so a cultural component that is quite important as well. And because of all the care that is needed throughout these circular processes, reuse is also a driver for jobs that are local, that are renewable, that are sustainable. So reuse is there. It's been in use for centuries. We're not doing it probably because designers have a fear of the unknown, that we are not used to it anymore. So the goal of this team and what I will present later, so the result from this team, is indeed to try to avoid or clear some fears of the unknown. So we started a bit naively because we are designers, and the first question for us was to check and indeed understand that it's okay if we don't know nothing about the materials. We don't need, as engineers, as architects, we don't need to know everything about the material, the given material, how it's behaving, all the mechanical properties, in order to build a structure that is structurally sound and safe for people. Because we were in Switzerland, we had access to thousands of skis that were thrown away, and we showed that these skis could be assembled as an elastic grid shell, and then combined with reclaimed flat panels as well. There is a lot of mass behind this assembly, but this is not the main focus of this talk today. Then we moved on, looking at structures made of steel and timber. With this one, with this first case study, showing that in the end it's an algorithm, a mathematical problem that could be optimized. If we want to reclaim the members from these old electric pylons that are actually being dismantled in valleys at the moment, and we want to, for instance, create this extension for the Lausanne train station, the roof at the train station, then there are three questions that we need to solve as designers simultaneously. The first one is what components are worth being taken from the sources. The second one is where to put them in the structure, and the third one is what shape to give to the structure. So it's a form-finding issue that can be tackled with tools. If you're interested, we have this Grasshopper tool that is freely available. It was used by this architect for reusing electric pylons indeed in this facade. We also showed that transport impact is not an issue. The savings related to reusing those components are so huge that it's okay to transport those components up to 500 kilometers, sometimes 1,000 kilometers. We also show that because when we are reusing components, you cannot optimize the cross-sections of those components. And so every piece is a bit oversized, but still this is not a real issue, and by replacing those components that are too oversized with newly manufactured one, you can reduce the environmental impacts further. And all that we did with steel, concrete, and skis, of course, was a bit irrelevant given the fact that the construction industry today is mainly related to concrete. Cement's responsible for 8% of global CO2 emissions, so all things considered, and 30% of construction and demolition waste. And here I want to make a clear distinction between recycled concrete and reused concrete. And when we speak of recycled concrete, it means that we are reusing old aggregates, and then we have to combine these old reused aggregates with new ones. We also have to add cement, as much cement as in new concrete, which means that the recycled concrete will generate as much CO2 emissions as a newly conventional concrete. And at the same time, there are existing techniques to take care of the pieces before recycling the pieces. So before crushing the concrete, we could cut the pieces and reassemble them. So extend the service life of those components before the recycling process. And this is something, it's not new. It was done. Here is an example from 1986 in the Netherlands, where this building was dismantled. It was made of precast reinforced concrete panels. So disassembled, sometimes cut, disassembled here, and here it's one of the many buildings that was built using those panels in the, as structural components. You don't see it from the outside, it's just there. Yeah, so what I mean here is that it's also economically viable as a strategy. As far as we were concerned, we were in Switzerland. There's not that much precast concrete in Switzerland. There is a lot of cast-in-place concrete. So first we were interested in showing that it would also make sense to cut reinforced concrete and reuse the pieces into new assemblies. So we started with this footbridge here. The pieces were actually dismantled from the basement of an hotel that was built 10 years ago only. So it wasn't a full transformation, it's just a local transformation. It made sense for those cutting companies to have small pieces because they had to move them up to the ground floor. And so we drilled those pieces and assembled them there. Of course, what matters is the life cycle assessment at the end of the process. And what we see here is that so this is the footbridge that we built. This is the equivalent bridge, but with newly cast-in-place recycled concrete here as a monolithic arch. This is the equivalent in steel and the equivalent in timber. So the reused concrete solutions decreases the other conventional solutions by 2 or 3, by a factor of 2 to 3, but also is very close to the timber solutions. And so probably that reused concrete is as green as timber. Timber is usually seen as the most sustainable construction material for structures, and here there is a new alternative to timber. We should increase the construction in timber, but we could also complement it with recrete, because this arch here has the same quality, the same behavior, the same properties as a new arch in reinforced concrete with new reinforced concrete. In terms of properties, it's just about the same. And that will become even more evident with the next examples I will show. This bridge is currently being tested on site in Vallis. And of course, in this bridge we're only using the compression strength of the concrete, but we know that in reinforced concrete there is also steel reinforcement, bringing bending capacity, and that should be reused as well. So we started with here with students who actually led the project. They managed to collaborate with industries, get the funding and so on, in order to cut those mushroom slabs and reassemble them here together to build a new pavilion that will be completed with straw bale walls, and now there is a roof structure already on top of that. This is available here, it's feasible, it's economically viable as well. And if you remember when I spoke about the 90% CO2 emissions, This is achievable with this solution in particular, where slabs are just being cut as slabs, reused, and applied in a new context with current norms, so answering all the norms and the constraints of today's construction. To achieve the same load, sometimes we have to be a bit clever by reducing the spans, for instance. But if we are reusing steel beams as well to reach the spans that we need, then we could build everything we want. And this reused solution for a slab is only 9 kilo CO2 equivalent per square meter. So there is no other solution on the market in research that can reach that low carbon footprint. And it's readily available. There is nothing new. The technique is there. The technology is there. And still, as researchers, we can also have fun. I mean, it's a boring slab to reuse as a slab. There is no change of form. And this is where we have the fun as the designers. But we can find the fun elsewhere, because now the design process also becomes a deconstruction, a careful deconstruction process. And so if we start, this is a case study done by another student, if we start from given buildings with their floor plans, there is a variation in the steel reinforcement throughout the slabs that we can characterize. Now the question is, what are the cuts that are needed? How to reassemble the pieces of the puzzles in order to meet the structural demands in a new given floor plan. And this is, again, a process that can be optimized and seen as a design question. And then to conclude, so this is a typical type of waste that we have. These are the slabs that we've been cutting to assemble as slabs pretty soon. But you see, I mean, this waste is also there, and then I mean the question is what to do with these rubbers. There are solutions that have already developed in other universities as well to tackle them, and probably more solutions is needed. As far as we are concerned, we are also starting to look at what is available by hacking current conventional industrial tools that we have. So I'm not against digital technology, but probably that we should be very careful about what the digitalization is allowing for the construction industry and its environmental impact as a whole. I think that Stefana Pasco will present later on, will also present a bit more about it. All right, thank you very much for your attention.